Okay, we can start. Haven't seen you in a while. Hope you're doing well. Are there any questions from previous lectures? Any questions from online people? Okay, in that case, today we're going to talk about various hazards associated with thunderstorms in extreme weather. So we'll first talk about heavy rain. And then we'll transition to hail. And then we will talk about downward. And then we will talk about lightning. And then we'll finish with tornadoes. These are pretty much exam questions also from this lecture. Except the first two are combined. This is separate, separate, separate. Okay? But you will see your questions in PowerPoint. And I will also send you now document with all exam questions. Now, there are many more hazards associated with, of course, thunderstorms and other type of weather systems, but there is not enough time to talk about them. Like heat waves, exposure to UV light, which is not thunderstorm, but it's hazard, pollution, and so on. Now, why is heavy rain so important? It's important because it can result in flooding. And flooding is very difficult to forecast because it's a combination of, atmospheric silence phenomenon, namely heavy rain, but it also depends on the properties of the soil, or rather land. You know, if the soil is very dry and wet, or if it is not soil to begin with, if it is not dirt, but asphalt or something else. So that's why you tend to have often flooding in cities, because you don't have natural drainage, and you have a lot of concrete that holds water. Of course, you have a sewage system, but if it doesn't work properly, as sometimes happens, then you can have a huge accumulation of water in very short period. And now, where you have different properties of soil, or whether or not some sewage system will work, it's almost impossible to predict. That's why it's so difficult to forecast flooding. Because even if you can forecast this, it's not the whole story. Okay? Now, this is the best equation in this course that says that precipitation accumulation over some region is the average rate of precipitation times duration of rain. So it says you will have a lot of rain if it rains hard for a long time. Okay, that's the equation. So in terms of heavy rain and potential for flooding, as you can see, we don't want to have heavy rain. But if we do have heavy rain, we don't want that rain to last for long. Or if we have long rain, we don't want it to be heavy. So quite often we have rain from these that I mentioned many times in this course, nimbostratus clouds. But that rain is quite often of low intensity. It can last for days and you don't get flooding. Because the soil can take up that water at a rate that is at least equal to the rate of precipitation falling, and therefore you don't get flooding. This is millimeters per hour. That's also quite often they tell you 1 millimeter of rain in 1 hour, let's say. Anybody has idea in their head how much is 1 millimeter of rain? Everybody has idea of 1 hour, but 1 millimeter of rain, what does it mean?
1 meter cube.
1 cubic meter.
1 millimeter cube.
1 millimeter cube, no. It's a take area 1 meter times 1 meter. Okay? And put amount of water of the depth 1 millimeter. That's 1 millimeter of rain. And you can demonstrate to yourself this is 1 millimeter of 1 millimeter. 1 millimeter of rain is also 1 liter of rain. So that would be, so when they say 2 millimeters and so on, it would be a cube of 2 millimeters high and so on. Now, you see, let's compare why we get heavy rain from deep clouds. That was one of the first questions in this course, and we don't get maybe deep. So let's take this nimbostratus cloud that we didn't cover in this lecture. But maybe this is the depth of the cloud. Here is the surface of the Earth. This nimbostratus cloud maybe has depth several kilometers. It spans hundreds and hundreds of kilometers. Whereas a thunderstorm, maybe let's assume for the sake of simplicity, has the same base, but it goes very deep into the atmosphere, and we said it can even reach tropopause, namely the border between troposphere and stratosphere. Here we have updraft. Let's just assume single cell, and somewhere here we have downdraft. And somewhere here we have updraft, and maybe between there were some downdrafts embedded. Okay. First of all, updrafts and downdrafts in this cloud are orders of magnitude smaller than in this cloud. Updrafts here are a few meters per second, if even that, maybe 1 meter, maybe below 1 meter per second. Downdrafts are even smaller, few centimeters per second or something like that. Whereas updrafts here are much higher. We said they can go over 20, 30 meters per second, but let's just say 10 meters per second. Which means when you have some condensation of liquid water, then these particles can be brought into a much higher region of the atmosphere where it's much colder than here. Well, much colder here means there is more potential you will have ice in these clouds than in these clouds. Once you start having ice particles, those ice particles additionally grow at the expense of liquid water. I am not going into microphysics processes of that. It's called the Djordje process, how ice grows at the expense of liquid water. But once you have ice, that ice grows so you have water vapor molecules. Water vapor molecules deposit on ice, that's called deposition. This ice is moving around, it's falling down, moving left and right. And as it is doing that, it is collecting supercooled water. You remember I told you supercooled water is water at negative temperature that is in liquid state. When that water touches ice, it freezes immediately. So you have this particle of ice collecting liquid water, that water freezes, so this particle of ice becomes even larger. It turns out, now imagine, you can envision the following situation, which happens. Imagine this particle of ice is heavy enough to be, let's assume, stationary at the same height. So in other words, updraft that is pushing it up is just the right strength so that this particle doesn't fall down. And because there is turbulence, of course, this particle is maybe moving left, right. And you can imagine it is vibrating left, right. Because this liquid water is much lighter because it's much smaller. That liquid water is passing through particle of ice, and the particle of ice is growing because as the water is passing, it gets accumulated on this particle of ice. Everything that I explained here doesn't happen here, or if it happens, happens in very small amounts. So eventually, when these particles of ice start falling down, they will melt. Because if zero, let's say 0 degrees is here, if 0 degrees is here, they have a long way down to the surface of the earth, they melt and they fall like big particles of water. Number one. Number two, again, we said that these updrafts are very strong. Strong updrafts do what? Here is boundary layer air, here is moist air. Strong updrafts bring moist air in the cloud at very high rate, very fast. So you have a lot of condensation over a short period of time. All these processes are happening in the higher regions of the cloud, and eventually you have precipitation falling at the surface at very high rate and very big chunks of rain droplets. Whereas here, this is not the case. Here you have small particles of rain, but because, sorry, these updrafts are very persistent, I didn't talk about, but these updrafts are associated with very large updrafts of air, hundreds of kilometers. They are weak, but they are persistent, forming this relatively weak. So this precipitation over here, as we already discussed, is called stratiform precipitation. This precipitation over here is known as convective precipitation. Okay. Now, if this cloud can last, for a long time, v duration, then you have a good potential for precipitation. But here you have to be careful. When we have duration, when we say duration v, we mean about the same region. Of course, if the cloud produces, because flooding is here, okay, so you need cloud to stay for a long time over Genoa, and that is this duration that you're talking about. Not duration necessarily of the whole lifespan of a cloud that moved from here to Slovenia, okay? Does this make sense? Now, when you remember we said that in terms of storms, we have cell motion, we have propagation, and then system motion. So imagine a case in which cells move in this direction with the mean wind. We said cell motion. Let's assume cell move like so. And let's assume that cloud propagates like so. Propagation, you remember, is development of new cells and dissipation of old cells. So when we combine these two, this is now a storm motion. We discussed this in details in our lecture on multi-cell thunderstorms and squall lines as well. So you see, these cases are quite prone for flooding because cell motion is kind of opposite to propagation, which means cloud is not moving a lot as a whole. Okay, it's not moving a lot. I didn't want to put exactly negative so you don't get anything, but something. So the whole cloud is just slightly advancing with time, which means it has potential to stay over a long period of time over the same location, and if the rate of precipitation is high, you can get very heavy rain that can cause some sort of flooding. Now, this average rate of precipitation, well, not average, but rather instantaneous, can be approximated in the following way. If you have moisture in the air, now this moisture is quantified to something called mixing ratio, but let's just say some moisture variable. Is that clear? This is some moisture variable. When I multiply this moisture variable with W, vertical velocity, I get flux of this in the vertical direction. Is that clear? In other words, here is the base of the cloud, here is the surface of the ground, here is W, that is positive clearly, and this W is transporting, this is times, transporting some moisture variable, but I didn't talk about mixing ratio, so just imagine that this is measuring how much moisture you have in air, okay? So this is amount of, this is cloud, this is amount of flux of moisture into the cloud. Well, what is rain? Rain is this moisture condensed. Now, in some ideal case, you could say that rate of rain, this rate of precipitation might be equal to this, because everything will condense and then fall to the ground. But that's not the case. So there is some factor called E, so-called efficiency of precipitation. Because, of course, not all of this will end up here and fall down. Some of this air will leave the cloud. Some of this air will evaporate and not fall as precipitation. Some of the cloud air will evaporate and not fall as precipitation. So this equation is kind of simple, I hope. Flux of water vapor into the cloud multiplied by some empirical precipitation efficiency coefficient can be used to estimate rate of precipitation. So you can then again go deeper into analysis of heavy rain and say, okay, if I have very moist air, well, that's good. If I have very strong updrafts, well, that's good. And if I have cloud that is quite vertically stacked, that's also very good for intensity of precipitation. So it turns out this efficiency of precipitation actually therefore decreases as the wind shear increases, as the clouds start being more tilted. Is this clear conceptually what I talked about? Any questions or from people online? Okay. Let's move to discussing hail. Okay. So what is hail? Hail is particles of ice that reach the surface, and in principle, for something to be characterized as a hail, it needs to be larger than half centimeter. Yes, half a centimeter. I know half something, but it cannot be meters. And it cannot be, I think, millimeters, so it has to be centimeters. Okay? So if the radius, and again, I'm not sure now if that.
Yeah.
Anyways, you can check. If radius or diameter is larger than 0.5, it's hail. Okay? Of course, hail can be much larger than that and then cause all kinds of damage. Hail is primarily issued for agriculture, where it can destroy huge amounts of agricultural crops, but also cars, private owners, and also then houses. It can destroy roofs. Hail is particularly damaging when it falls in the environment with strong winds. So when you also have advection of hail, when it doesn't fall directly down, but also under an angle, because it can destroy more. It can destroy windows, sides of the buildings, and so on. Okay. Now, as the book says, most people are smart enough not to go out when you see large hail. So not many people get killed by hail these days, but you could, in principle. And animals, sorry, they are more often killed by hail than humans, of course. Now, how also terminal velocity of hails can be very large. So what is terminal? Anybody knows what is terminal velocity? No?
Velocity of one particle of ice.
Yes, but there is one catch in that. It is, but what exactly? It's the velocity of the falling particle that is in equilibrium with the drag force that is exerted on it. Because when you release this, it accelerates. Okay, like when you jump out of airplane, let's say without parachute, for sure you will die, but you will first accelerate, and at some point you will not accelerate anymore, because force of gravity is equal to the drag force, and you're just moving without acceleration down. The same happens with hail, right? So you have a particle, let's assume just a sphere. Most hail particles, if any, are not perfect spheres, but many of them are like spheres with some protuberances, with some irregularities. So if this is height z, then you have mg acting down, and you have drag force acting up, right? Everything okay, Yossi?
Yeah.
Ah, I thought you were the time.
No, I gave you a nod.
Yeah, so FD is, anybody knows the equation for drag force? Come on, wind engineers here. This is
Rho, CD, basic lengths.
row of what?
Yes,
Row of ice or row of air?
not there.
But why row of air? It is row of air, you're right.
Because of the Reynolds number.
Yes, because the air is passing next to, it's not, nothing is passing through this cube of ice. The air is passing next to it. Yes, you're right. Times A, right? Where A is cross section in the direction of falling, times drag coefficient times terminal velocity squared. And now when you equate these two, you'll get the terminal velocity is equal to mg divided by rho A times CD. Of course, you can simplify this further because m you can express as density of ice, because this is now mass of ice, times 4/3 radius cubed times pi, and then this A, because this is sphere, is pi r squared. So you can plug in these and simplify. Anybody knows drag coefficient for a sphere?
It's a function of velocity.
Yeah, but we're very high on this number yet. Yeah, it's a trick question. It's function. You know that I don't know, something like this, right? And here is Reynolds number, and here is CD. But in so it's you know, you have to, I have to tell you Reynolds number for you to tell me drag coefficient. But in the conditions here in the atmosphere, it's usually around 0.45. Okay. Okay. So these terminal velocities, if you plug in numbers here, some reasonable numbers can be 30, 40, 50 meters per second. So you don't want hail of 100 grams to hit you in the head at this high velocity, or to hit your car or something like that, okay? Any other question? Any question?
Let's see, is theoretical or is it experimental?
Like experimental. I think they measure. Because again, well, theoretical is 0.5, right, for sphere. I think.
Yeah, it's,
Yes. So, because it also, you know, you have all kinds of hail, but even more importantly, you have hail that starts melting, so it has liquid water around. So you have a film of liquid water. You remember when Professor Solari also talked about this problem? If you have a bridge that has suspension cables, and okay, you analyze the behavior of these things under wind loads, but then if you have rain and you have a film of water around these cables, and you have wind, then water elongates, it completely changes the shape. One might think, maybe naively, water will just be swiped off, but it's not swiped off. It stays there, but changes hydrodynamics. So the same is you see happening kind of here. So it's very complicated to measure. Very, very complicated. I mean, there are infinite numbers of shapes, but this is approximate. What I found in books. Okay. Now, how does hail form? How hail form? It also forms in thunderstorm clouds, particularly in those thunderstorm clouds that where 0 degrees temperature is very close to the surface. So when the hail leaves the cloud, it doesn't melt before reaching the surface. Okay. You see, the most common place where you will find storms is in the tropical region. Tropical region is full of thunderstorms. But rarely you get hail. Why do you, what? If somebody would ask you, how is it possible you don't get hail in tropical regions, but you get hail in North America, Canada, Europe, and so on? That's because air over there is so warm that 0 degrees is very far from the surface, and then when the hail starts falling down, it melts. So it ends up with being precipitation. Okay? So there are still a lot of research papers looking into how hail forms, because we have some conceptual models, but some of them are not always correct in reality, at least measurements show. But one of the typical models is you have thunderstorm that looks like this. Here is the surface of the earth. So this is height, vertical cross-section of the thunderstorm. You see, we have this updraft that might look like this. Okay? Cloud means now water is condensed. Now particles of water go into the upper regions of the cloud and they become ice over there. Okay? Now this ice over here, I usually do this. I actually have very nice slide in PowerPoint to visualize this. But I also have this beautiful blackboard, so I can visualize here as well. So let's take this is position 1 of the ice. Okay, this ice particle thanks to the position, namely space. Now this ice particle is moving left and right, and it goes into this part of the cloud. But here, updraft is weaker. You can see that updraft here is vertically up, strong. Here, updraft is weaker. So this particle of ice found itself here. Okay. And now, because updraft is weak, it falls down. Maybe it would be better if you have different colors to indicate trajectory of hail with different colors. I don't have different colors, okay? So this particle of hail falls down, but look, it is falling into updraft. So it falls into updraft, and updraft is stronger here than here. So it finds itself in this position 3. From position 3, it is brought up to maybe position 4. Okay? So you see how it is circulating. As it is circulating, it is collecting water. It is collecting water and growing. Now, you can also see it's very important that 0 degrees is not somewhere, is not here. Because when this guy falls down, it starts melting. It's very important that 0 degrees is maybe here, or I don't know, some as lower as possible. So as it is making these circles, it is constantly negative temperature, so it never melts, it only grows. And again, I apologize for not having enough time, but you have to trust me that ice always grows in the presence of liquid water and water vapor. That can be theoretically demonstrated, but you can just take it as granted, okay? So the more circles this particle of ice makes, the bigger it can get. This also explains to you, hopefully, why you get hail only in these strong storms where you have strong updrafts. Because let's assume this is weak updraft. This particle falls from location 2. This is not strong enough to catch it. It just falls down to the ground, and in the meantime it melts. Because it was very small, it was the first fall, so it was very small, it will just melt down and fall to the ground. In autumn, let's say, most of the rain that falls here usually starts as ice in some upper regions of the cloud. Okay, but it melts. Not necessarily in summer, but in the colder parts of the season. Now, eventually, just as a product of probability, this particle will find itself here. Maybe it grew to a very large size, and now when it falls down, there is nothing to catch it, and it just falls to the ground. So you can also see that hail, large hail, is usually observed close to the updrafts. And I will also mention one more time, it has been demonstrated through numerical modeling as long as some measurements that if you have turbulent atmosphere here, and it's always turbulent because there is very large shear in the W, so that hail is traveling horizontally a lot. You know, if it is zigzag a lot, that helps a lot because it stays at the same place for a long time, acquiring huge amount of liquid water, okay? And that is because big particles of hail have relative velocities different from liquid water. Liquid water is smaller, although water is denser than ice, but it is also, these particles are smaller, so it's lighter and therefore it moves fast next to the hail, and some that catch the hail get acquired, not all of them, there is also efficiency of that, but anyways, the hail grows. Does this make sense? Now I'm not going to do it here for the sake of time, but now when you go back to your lecture on supercells, and you plot flow field in a supercell, try to figure out where are the regions of largest scale, and then next to the largest scale there is heavy rain, and then next to a region of heavy rain there is, I don't know, moderate rain, then there is a region of light rain, and then I don't know, you know. So based on what we discussed here, go back to that lecture, check the schematic of a supercell thunderstorm and try to reason where you would expect the largest scale to occur. Any questions from you or online people? Yes.
If we say that it's more common to have a when the zero temperature is not so far from the ground. So why it occurs more, I mean, I suppose it is occurs more frequently during summer instead of that is more cold.
Yeah, that's a very good question. That's a very good question. Because during winter, it's very cold. It's too cold for here. When temperatures are so low in high regions of the cloud, you actually don't have that much supercooled water over there. So you get a lot of ice crystals in the cloud. Okay? You have huge amount of ice crystals. And you see, imagine now these ice crystals come together. They will fall, they will form something as ice flake, snowflake. Okay? So snowflake typically grows through something known as aggregation. Aggregation is when ice crystals come together and stick. Whereas hail typically grows through accretion. Accretion means you have, let's say, this ice crystal, but this ice crystal is acquiring liquid water. And that liquid water is, as I said, super cooled liquid water. So that super cooled liquid water goes here and then freezes. And then next layer. So also when you take, and also now it's a theory of cloud microphysics. Prevailing method of ice growth also depends on temperature of the environment. If the temperature is very low, this is not very efficient. If temperature is not very low, this becomes more efficient and so on. Okay.
Okay.
Okay, we have 5 more minutes to discuss downbursts. And there are people here doing research on downbursts, so clearly there is much more to say than what I'm going to say in 5-10 minutes. But we will go again to this thunderstorm cloud, surface of the ground. We have downdraft in this precipitation region. We have updraft, like so. There is also a downdraft here, but very weak. There is downdraft here. Downdrafts are generally everywhere around the cloud. Weak downdrafts. That's why thunderstorm clouds tend to be isolated. Because you don't get some new cloud over here, there is some downdraft spilling. But there are very strong downdrafts in the precipitation, sometimes in the precipitation region of the thunderstorm. Now, in the region of very cold downdrafts, you often also have very strong precipitation. But when these downdrafts hit the surface, they spread radially, like so. And they spread radially, producing this outflow in the form of gust front. We said gust front is the leading edge of this outflow. And these winds can be very high, okay? Very strong winds. Now, downbursts are generally separated into microbursts and macrobursts. Now, in some books, you will find definition that the radius of this outflow has to be below 10 kilometers to be downburst. Okay, not all books cite it. But generally, they say, look, you cannot now, if it is too large, then most likely it's not too strong, so it's not downburst. So generally, this over here should be below around 10 kilometers. Okay. Now we further subdivide them into microbursts and macrobursts. Now, this is completely empirical subdivision. Microbursts are below a radius of these damaging winds. Of the zone of damaging winds is below 4 kilometers, and macroburst is above 4 kilometers. But clearly less than 10 kilometers over there. Okay? And then we can further subdivide them into dry and wet. Dry downbursts, well, let's first actually say wet. Wet downbursts are more typical. They happen when this precipitation reaches the surface. If precipitation evaporates before reaching the surface, these are called dry downbursts. Again, you can immediately conclude that dry downbursts are more common in cases where the cloud base is very high. So precipitation is falling through very deep region of non-cloud air. Whereas if you have cloud base that is very low, well, then it's more likely you will have wet downbursts. So that also means close to the sea, wet downbursts are much more common because air is very moist. So the cloud base is very low. Whereas deeper inland, probability of dry downburst is more high. Any questions about this? Well, now the question is, what is causing this air to go down? What is causing air to sink? I mean, we already discussed some of these things in the very first lecture. It's negative buoyancy, right? You remember that buoyancy force, B, that we derived? That's one of the exam questions. So these downdrafts are negatively buoyant, we would say. In simple layman terms, they're colder than the surrounding air. Okay. But I don't know if I should ask you this question now, or I save this question for the exam as a subject. But we know when the air is going down, remember adiabatic heating and cooling of air. We said when the air is going up, it's cooling because it expands. But when the air is going down, it actually warms because it contracts. So why would this be cold if the air is going down and naturally it actually warms? But we just claim this is cold with respect to the surrounding air. How does one explain that? Is that clear what I'm saying? When the air goes up, it cools. When it goes down, it heats naturally. But in this case, we are saying it's going down, but it's cooling. Any concept of latent heat that we discussed?
Because for condensing, heat was
Released or valued at 50%? Huh? Is condensation releasing heat or taking heat?
it's releasing.
It's releasing. That is correct. Condensation is releasing heat. But what is happening in the downdraft? Do you have condensation or something else?
We said evaporation.
You have an evaporation, and evaporation is taking heat. So in principle, yes, this air is warming down, it's warming as it is falling, but it is cooling due to evaporation, and the rate of cooling is much higher than the rate of warming due to adiabatic processes. So overall, you end up with cold air. Does that make sense? So the phase change is once again extremely important. In other words, the phase change that increased temperature of the environment over here results in the decrease of temperature in the downdraft because you have evaporation. Why would you start having evaporation? Well, you start having evaporation because first of all, there is entrainment instead of dry air into the storm. In the back of the storm, you have some volume of dry air being moved into the cloud. It starts evaporating this region and you start having downdraft. That's one reason for downdraft. What would be another reason for downdraft? Another reason, remember, there are particles of rain and hail and I don't know, maybe even few snowflakes over there, who knows? They are all falling down. They exhibit drag on the air. That's also known as precipitational loading. As the air is falling down, it drags, just like when a train passes next to you, you shouldn't be very close because it can drag you together with it. So the same is happening here, okay? I will stop here because there are some other processes, like some vertical pressure perturbations and so on, that are very important for these rear flank downdrafts, if you remember in supercircle. But these are at least the basic mechanisms that you should know, okay? So let's just then discuss what is happening once this downdraft hits the surface. So first of all, if you assume that this cloud is not moving, and this is XY direction, imagine this is downdraft of diameter d. Once it hits the surface, it spreads radially equally in every direction, right? So that gust front of downburst is spreading equally in every direction. But if the cloud was moving, let's say from left to right, then there is a downdraft, let's say downdraft hits here of radius d, of the diameter d, then it typically spreads predominantly like so. Because it already had initial momentum in the direction of this cloud motion, okay? So it's skewed. More common, you observe this in the atmosphere than this. Never clouds are perfectly steady and whatnot, okay? So there are people here in this classroom analyzing this and studying this for getting PhD degrees and whatnot, okay? I see you're not very impressed with that. You're saying that, what is this? You're studying that for PhD? Talk to Dr. Jalan. Yes. And the last thing is what is the vertical profile of winds? Okay, you remember in the first lecture we said that winds in the atmospheric boundary layer, in the atmosphere in general, I didn't talk that much about atmospheric boundary layer winds. Let's say here is mean wind, U average. They generally logarithmically increase with height. This is non-downburst. Again, many people call these atmospheric boundary layer winds, but I didn't talk that much about atmospheric boundary layer, so let me just call them non-downburst winds. But in the case of, so they follow this log-like profile. Very big change close to the surface, and then not so much at high elevations. You can imagine somewhere here being approximately height of 1 kilometer. Okay, so you have some order of magnitude what I'm talking about. But in the case of downbursts, winds have this nose-like profile. See, this has nice mathematical function, logarithmic-like, and this has anatomic function, nose-like profile, where here is Z, and here is, let's say, U average. Okay, so the maximum is close to the surface, usually between 50 and 150 meters above ground. And therefore, U maximum, I mean, is close to the surface. Whereas U maximum here is at 1 kilometer. And you should know what are these winds at 1 kilometer because we covered them in the first lectures, gradient, geostrophic winds, and so on. And the very last thing I will say, I know I went 4 minutes over time, but that's fine. the last thing I will say, why do we have this profile with downburst outflows? Well, that's because if this is the surface of the Earth, and we said we have this downdraft, in simple words, this downdraft, let's just look this direction, spreads radially, but it spreads over certain depth, h. Okay? Just like, I mean, almost like when you spill water, it just has a certain depth over which it spills over the surface. So you see, wind speed is increasing with height up to certain level in this layer of the outflow, and then it decreases with height, and maybe here is constant, and then who knows, maybe it increases, it doesn't matter that then you are not anymore in atmospheric boundary layer. Make sense? Of course, profiles, when you measure them, are never perfectly like this. So you, because this is at the end of the day, you average, but even in the average sense, you always have some wiggles, but this is overall the profile, okay? Winds in downbursts can be very high, not as high as tornadoes, but they can exceed 40, 50 meters per second, which is very, very high, very close to the surface. And if this is at 50 meters, and you have some building here, then clearly this represents a potential hazard for your structures. Any questions?
What's the threshold?
Threshold for downburst.
I mean, we can say that every time there is a thunderstorm.
Yeah.
There is a downdraft, so
Yeah.
what's the,
That's a good, there is no, to my knowledge, official threshold for downburst. For example, I think Fujita used 10 meters per second. So different researchers can use different values. But for example, I know in the US storm database, if this downdraft causes damage, it's downburst, okay? So if it is causing some damage, now it doesn't have to be damage, destroyed half of the city. It's just few branches of the tree, somebody noticed. They call it downburst, okay? But you are right. Every thunderstorm has downdraft, but most of the time these downdrafts are not so strong, so the thunderstorm just passes. But you will notice every time thunderstorm approaches, wind speeds pick up. Well, they pick up because of this. Any questions from online people? What, I see now. What are the conditions that contribute to the formation of large hailstones? I discussed that, for example, if you have multiple circulation, multiple paths, okay? This is great, by the way, but I'm answering questions. So if you have this storm, here is the surface of the Earth, and here is, I will just simplify, here is updraft that spreads like so. Now you take this hail that was moved here, then falls here, then is caught in the updraft, then travels up, and you see it will circle like so. If it circles a lot, it has big potential to grow to become large hail. Okay? Secondly, you will also remember we said that this hail grows by acquiring liquid water. So if the liquid water content in the cloud is very high, you have very high potential for hail. Secondly, if 0 degrees is very close to the surface, then this hail, now it grew to this size, when it falls down, there is only a short distance that it travels in positive temperature regime. So again, it has large potential to be large when it falls to the ground. And also, there is temperature dependency. As I said, there is zone of temperatures when this particular rate of growth of hail is very dominant. So these are temperatures that are negative, clearly, but not very, very low. Because if they are very low, you go into a regime of snow. Does that answer your question? Well, okay, I will assume yes, but okay, thank you. Okay, I will pause. Recording. So, last two topics in today's lecture are lightning and tornadoes. So what is lightning? Basically, it's a channel of electrical current flowing through the atmosphere from, and what we will talk in today's lecture is generally from thunderstorm cloud to the ground. Because you can have lightning between two thunderstorms. You can have lightning within thunderstorm. That's called cloud. You can have lightning from thunderstorm to ground. That's called cloud to ground. And you can also have lightning that develops at the ground and moves into storm. That's ground to cloud lightning. But most lightnings have been in the cloud, actually, inside of the cloud. But they are not of interest for us living on the surface that much. So if we look into ground to cloud and cloud to ground, lightning cloud to ground dominates, okay? Around 95% of lightning strikes are cloud to ground compared to the other way around. I would assume nobody here has a fur. Nobody has a fur? It's not winter, so I don't think anybody. Like cat's fur, or when you have a jacket with fur, no? No. Because I usually demonstrate lightning using fur. And that requires beating up students, which gives me great pleasure. So when you combine these two, you get very nice demonstration. But I don't have cat's fur or rabbit's fur, so we'll just go to theory. Okay. So to get lightning, you have to separate charges. Okay. As you can see, when I touch this desk or I walk around, everything is neutral, so I don't get electrified. But if I touch wire in the wall, I get killed because there is a potential difference between us. Now, very important to know is that air is very poor conductor of electricity, very poor, especially dry air. And you know that, maybe you didn't think about it, but speaking of these electrical wires, how many times electrical wire is on the ground? Maybe they say open live current on the ground, and you walk next to it, it doesn't kill you. It doesn't kill you because the air is so poor at conducting electricity. But if the situation was this, let's say this current, there is current in this wire, very strong current, and I stand here, nothing will happen. Now we just replace everything in water, I get killed right away. Or I connect metal between these current, the wire and me, I get killed or injured. So air is very, very poor conductor of electricity. Now, eventually everything conducts electricity if the voltage potential is large. Okay, so if I run, let's say I have zero potential, and I run current here, nothing happens. I increase voltage, I increase voltage, I increase voltage. At some point, there will be a spark between this wire and me. When will that happen? That will happen at a situation that we call breakdown of air. So electric breakdown of air happens when the field is about 3 times 10 to power 9, I think, volts per kilometer. Or power 6. If anybody has Google, they can Google, okay, I forgot. So if voltage per kilometer is this big, you get air starts being conductor of electricity. Now, when air is conductor, what is air? We have to look into. And this is moist air. Sorry, this is dry air. For moist air is a little bit lower. So you remember that air, now we don't look into continuum anymore. We look into molecules and atoms of air. So they have, an atom has positive core and electrons that are negative roaming around. Of course, in quantum mechanics, they don't like when you say they're circling, orbiting around, but anyways, for this purpose, it's fine. And this is maybe hydrogen. And then you have oxygen. So oxygen would have how many? It would have 8 protons, I think, or something like that here. 1, 2, 3, 4, 5, 6, 7, 8, and 8 electrons orbiting. Okay. So these are atoms. Now, if you apply very high voltage, this electron likes to be next to this proton. And there is Coulomb force that is attracting them, right? But if I apply extremely high voltage that is high enough to strip this electron from proton, then I will end up with proton being isolated and this electron being isolated. Okay? So if I strip all these electrons from the core, then I will end up with what they call soup of positively charged particles and negatively charged particles just floating around, but they cannot come together to form atom because electric field, external electric field, is so high that it overpowers Coulomb force between these elements. This state of matter is known as plasma. The sun is the plasma, okay? So you have 3 electrons and 3 protons and neutrons floating around in the sun. So at this strength of electric field, the air becomes plasma. And when you have plasma, then you have moving charges, and these moving charges are current, okay? And plasma is very good conductor. But to create plasma in the air, you need this value of voltage per kilometer. Okay? Very high. And as I said, I think it reduces to 1 times 10 to the power 9, 6, I forgot, as I said, check it when you're in moist air. Okay, so that's kind of how air, and you also kind of know this in this example that I talked about, because when you're passing next to transmission lines, there is a sign, do not climb. They don't tell you do not climb because you might fall and die. That's one reason. But another reason is you have extremely high current running through, extremely high voltage in the transmission lines. And then as you're getting closer and closer to the transmission line, you might exceed this value. And then you have what? You have here surface of the ground, you have a transmission line going like that, you are safe here. But when you climb here, you're very close, so you might connect. There is arc. The air becomes plasma, current flows, you get, well, I don't know what, injured. Let's put it like that, okay? So not to be too morbid. Okay, so that's what is necessary for air that is around us to conduct electricity. But how do we get these huge electric fields in the atmosphere? Well, we get it in the presence of clouds. Now, clouds that separate charge, so you need to separate charges, separate positive from negative to get voltage. The only clouds that can separate charges to the extent where it matters are cumulonimbus clouds, again, thunderstorms. And the process of charge separation is actually not perfectly known. There is so much research in that field. Now, generally, atmosphere is positively charged and the surface of the earth is negatively charged. This is called fair weather. Electric field. But this is also something that is extremely difficult to measure because this depends on where you are. Probably, if you measure the electric field in this classroom, maybe it doesn't satisfy you because you have so much electricity running around that dominates this field. But if you maybe go in the middle of some field, somewhere far away from all electronic devices, and the weather is nice, this is typically what you observe. Now, but we are not in fair weather, and usually this strength is 100 volts per meter, strength of electric field in fair weather. But in cloud, thunderstorm cloud, we have hail that is falling down. Okay, I'll take this as a, I shouldn't say hail, I should have large particle of ice. And then we have some smaller particle of ice. Like so. In principle, smaller particle of ice, let me make it bigger so people online can see it. Smaller particles of ice are usually more irregular than big particles of ice. So maybe even better, I represent this as a speed. But doesn't matter, you don't have to correct it. Okay, it doesn't matter. Now, from research, people established that for most temperature regimes that you find in the cloud, at the spikes of these small crystals, you have negative charges. Okay? So let's say this guy is neutral, of course. You have two negative charges, and let's say you have two positive charges. It's neutral, right? This one has, let's say it's bigger, has 3 positive and 3 negative charges, like so. And this one is going down, this one is going up. This is relative to each other. This one is falling down, this one is going up. This one is going up because it's small. You remember, small particles of ice go up, bigger maybe fall down. And they collide. Now they collide, so from this condition 1, we moved into condition 2, which is basically after collision. So they collide somewhere here, and after collision, this particle is here, and this particle is here. This large particle tends to acquire a negative charge from a small particle. So you will have 1, 2, 3, 1, 2, 3, 1, 2, 3. But it also acquired 1 negative from this particle. So these small particles ends up being, as you can see, one negative and let's say two positive. So it ends up being positively charged, this one ends up being negatively charged. Now, the process of transfer of charges is very complicated in a matter of research. Generally, very small amount of charges is transferred like this. In a typical collision, only about 100,000 electrons pass during the collision, which is really nothing. Because I think 1 coulomb is about 10 to 23 or 18 something electrons. Now, is it 23 or 18? Doesn't matter, but it's huge amount compared to this. So way less charges than 1 coulomb are transferred. But thunderstorm is huge. Okay, so in 1 square kilometer, you get an enormous amount of these collisions. So you multiply 100,000 by enormous amount of collisions in 1 square kilometer of a thunderstorm, and you get that huge amount of charges is separated in this way. Is that clear? Now, what we end up with is that here, if we have a cloud, bottom regions of the cloud tend to be negatively charged overall, as well as middle regions of the cloud, whereas top of the cloud tends to be positively charged. Okay? Now, this is probably one of the biggest unknowns in atmospheric sciences is separation of charges. This is such a rough picture. Every time people do measurements, they discover something else. So please remember that this is not as clean as this. In reality, if you read books, when they do these measurements, you get patches of positive charges. It's not like this, okay? It gets more messy. And people are trying to figure out what are the mechanisms that are separating charges. But what is clear is that you have to have very strong updrafts in the cloud, because strong updrafts facilitate large relative velocities between large and small particles. Now, if you study electromagnetism, then you know if this is negatively charged, I have to do nothing. Surface becomes positively charged. If you are negative, I'm positive right away, okay? There is no other way. Because even if I'm neutral, I'm positive with respect to you. So you have this separation of charges, okay? Now, this mechanism and other mechanisms in cloud can be so significant that they can create these huge electric fields that result in air breaking down and becoming a conductor. Research suggests that lightning usually starts within the cloud, namely, these negative regions, maybe by chance, there is a pocket of positive region over here, somehow ended up. So you have discharge like so, from negative to positive, okay? Now, once the discharge starts, it starts propagating towards the surface because surface is positively charged. Okay, is that clear? Why is it going down? It's going towards positive charges. Current. These steps that the lightning channel is making are known as stepped leaders. They are leading by steps. Okay, I might misspell, but step leader. Okay, they are leading by steps. Each step that this lightning makes is about 50 meters. Okay, so it propagates 50 meters. And propagates these 50 meters in approximately 1 microsecond. So in 1 microsecond, you go approximately 50 meters. And then when it gets here, it takes about 50 microseconds to make next step. And then, so this step is made in 1 microsecond, and then it waits 50 milliseconds to charge, to get more charge, and then, and quite often you have branch. Now this is completely random, because what's the name? Lightning, as you can see this before, can see only 50 to 100 meters ahead. So when the lightning strike starts, it doesn't know, so to speak, where it will end up. It propagates 50 to 100 meters. When it gets to about 50 to 100 meters above the ground, you can see as this is going down, there is huge amount of negative charge pouring down like river. So you get huge amount of positive charges being accumulated close to the surface. And you get something called connection. And that connection transfers positive charges to negative charge, to this channel of negative charges. This is called streamer. Okay, not beautiful streamers online. I thought this joke would be more funny, but anyway, yeah. It is what it is. This streamer connects positive charges with negative. Is this clear what I'm explaining? When these two connect, you have that's like short circuit. You have very bright lightning. That's what you see with your eyes. With your eyes, you usually don't see this propagation now. I was very tempted to include a few slides to show you that, but just go and Google propagation of this, and you will see beautiful pictures. So this is called streamer. When the streamer connects with step leader, you get something known as return stroke. Okay. During the return stroke, huge amount of negative charges is discharged into the ground. Many coulombs. I mean, many, 2, 3, 4, maybe 10 coulombs. You know the coulomb is huge unit, so creating 1 coulomb of charge here, good luck. But 4, 5, 6 coulombs are transferred. As this is happening, you see this cloud is also huge. These other charges can move because this is now a conductor, it's plasma. This is plasma. These other charges can move here and discharge to the same canal. These are called dart leaders. So I know this step leader is the first canal that is going down in steps, like so. Streamer is what separates from the ground to connect. Once these two are connected and the charges are going down, that's return stroke. And the next discharge, if there is enough accumulation of negative charges here, is called dart leader. Dart leader doesn't branch because it doesn't need to go and search where to go. It already has established path. So it goes very fast all the way to the ground. Huge currents, 30,000 amps can be generated in lightning. Some of the largest measures, 120,000 amps current. That's enormous, okay? And of course, now if you are somewhere here, it's not good. So it's also not good next to some spikes, because at the top of a spike, you have huge amount of positive charges. I hope you can now imagine it, because if you have something like this, then these positive charges are still densely populated, but but if you have something like this, then all these positive charges are here. So it's more likely that the lightning will strike tall regions above the ground, tall obstacles than flat. That's if you see isolated tree, you shouldn't go next to isolated tree. But if you are on a field, because the laws of physics don't care about your life, if you are here on the field, far away from the tree, then you are the spike. You don't want to be spiked. So what do? I don't know. I read, they say the best is to estimate the height of the tree. So imagine this is the height of the tree, you put it down, imagine tree falls, you go average height of the tree, okay, and you kneel. You don't put your knees on the ground, you just kneel. So you're not close to the tree, but you're not far away to be spiked on your own, and you hope for the best. If you are walking in groups, you don't walk together, you separate. So if lightning hits Dr. Jelly, it has spread to all of you. Okay, these are morbid but regular. Okay. No, I know you the best. So if I select one of them, they might sue me. Okay. Does that make sense? Also, you shouldn't be next to electrical outlets in your house as well. There are many things I could talk about lighting, but I have to start here. Sorry about that, because we still have tornadoes coming in 15 minutes. Any questions about this? I know I have one statistics. Oh,
But if I am the spike in the ground
yes,
and I have some shoes.
Yeah.
That are,
yes.
it doesn't matter if I have the rubber shoes.
Current in lightning can be 100,000 amps. Okay. It can be 10 to 6 voltage difference, 10 to 6 volts. Now you take your rubber shoes and you touch 230 volts, and it's not going to end up good. Okay. Your rubber is isolator. These are huge currents, and everything is conducted at these currents. Okay. Okay. But there is one statistics I wanted to share with you. You know pie charts, pie chart. Research in the United States of America suggests this 70, this is 70, right? Yeah. So this will be 50, 75, okay? Percentage of people killed by lightning. In the day page of equity, diversity, and inclusion, it seems that more than 70% of people killed by lightning are men, and only 30% of women. How is that possible?
Because
That's so knows, like, this is a woman, I'm gonna skip it and kill that man over there.
Because women don't go out if there is a thunderstorm.
There are two reasons, that's number one. Reason number one, I can directly relate it to Dr. Djordje. Men are macho, okay? Particularly when they are next to a woman. So if there is a storm outside, and but this is you're laughing, but this is real data. Okay, this is true. And maybe Alessia said, yes, we shouldn't go out. There is a strong thunderstorm. Of course, Josip will say, thunderstorm can do anything to me. Me and my friend in Croatia once climbed the top of the cloud and whatnot. Okay, so men don't want to accept risk. They cannot say I'm afraid. Yes, maybe we shouldn't go. Okay, that's number one reason. But reason number two is men also work in more dangerous jobs. They work in field. They work in construction. They work on roads where you cannot find easily shelter. So it's more likely to be hit. Okay, so there is psychological reason and there is, I don't know, sociological reason. Okay, I don't know, this is for US, I don't know how it's in the other countries. Okay. Okay. Yeah, also, yes. When is it most likely to be hit by lightning? This is also, I don't know now. Here is probability of being hit by lightning. This is most likely being hit by lightning. And here is, let's say, time. It turns out when here is maximum of the storm activity. Okay, here is maximum of lightning outside. This is actually not where you are most likely to be injured or killed. Storm intensity get killed. Okay, get killed. It's more likely to get killed before, because you see, this storm looks like that. Now, I describe lightning from here, but lightning can also come from here. And when lightning comes from here, there is more chance to be ground to cloud. And ground to cloud is about 20, 30 times even stronger than cloud to ground. So if you are here, and you see lightning in the distance and storm is approaching, and you see, I'm safe here. And then you are in this region where it's very likely to be hit. Okay, because once in a while there can be a lightning strike that will, I mean, kill it. Well, you get the point. I'm talking about killing too much, but you get the point. And here also, when the storm passes, storm passed, you're like, okay, I'm here now, but there can be also lightning from the back of the storm. Okay. Okay. We have 5 more minutes. So let's just skip tornadoes in that exam question, okay? And that's not, I don't have in 5 minutes enough time to cover it. So I will remove it as an exam question, but if you want to study more about tornadoes, you're more than welcome to stop by my office and ask me, okay? Because it took me to explain lightning more than I thought. Maybe I over-explained it, but at any rate, we will skip tornadoes. So next lecture will be on modeling. I will talk a little bit about measurements, although that's not modeling, but that's like setting the stage. Then I'll talk about numerical modeling, as well as modeling in physical environments like wind tunnel, cloud chambers, maybe. But that will be a very short period of time. I will mostly talk about statistical modeling in Monte Carlo, simulations of risk and hazard associated with severe weather. Okay. So indeed, if you want to know more about tornadoes, you're more than welcome to stop by my office and talk to me about that. Any questions? Any questions from online people? Is it possible that lightning can strike same person twice? Of course, this is also one of these beliefs that has nothing to do with reality, that there is lightning never hits same spot 2 times. I think in one day, again, I read it some time ago, the Empire State Building top, during one thunderstorm, it was hit like 30 times, they measured it. So if you were hanging on top of that pole, you would be hit 20 times. So this is not true that lightning cannot hit same location or person 2 times. Also, thunder is the sound associated with lightning. And it's associated because temperature in the center of the lightning. Okay, maybe in these 2 minutes I can talk about that. So if this is the center of lightning strike, that channel, okay, I just zoomed in. So I said it looks something like this. But when you zoom in, you get this temperature here can be 40,000 kelvins. That's huge temperature, because temperature, you know, on the surface of the sun is, I think, 5,700 Am I right? Let's say 6,000 kelvins, and it doesn't matter. 6,000 kelvins is 40,000 kelvins. So it's huge. So when you have such a high temperature, of course, you can create enormous pressure here. So this expands. And it expands so significantly that it's above sometimes Mach 1 or so. So you get sound wave that propagates. And if you are here, you can hear it. Now, another thing is, when do you hear? When do you hear? Actually, it's not so easy theory. When do you hear thunder associated with lightning? Here is, let's just put idealized. Here is cloud. And you know the temperature is decreasing with height. Here is warm. Here is cold. Right? Well, sound propagates much faster in warm air than cold air, because warm air jiggles more than cold air. So sound tends to propagate down more than radially also, because here is cold. So if sound is a wave, it's a longitudinal wave, so it doesn't oscillate like this, but it, oscillates like Egyptian walk, forward back. So sound hits the surface and then reflects like anything. So you can see, if you are in this region, you will hear, thunder. But if you are in this region, you will not hear thunder. Of course, this is if the region is not flat, then there is a mountain effect and so forth. But now, what will be the angle of this? It's very difficult to say, because it depends on temperature specification in the atmosphere. But it really gives you some idea how the propagation works. Of course, you have something will propagate here as well, but much less than here, because propagation of sound on cold wave is diminished compared to warm. Make sense? And then, of course, there is this classical that they teach in kindergartens. Like if you count after lightning, you can determine how bright it is, because light pretty much instantly travels, but sound travels at 330 meters per second. So 330 meters per second times, you counted 1, 2, 3. 3 times 3, so distance is 900 meters. Rather 1 kilometer. Not 1 kilometer like that, 1 kilometer like that. Or how you saw it, okay? Anyways, I'm not going to ask you this in exam. I think I'll fill out these 5 minutes of lecture, okay? Any questions? Lying down, okay, can we talk about tornadoes next lecture? Unfortunately, no, because I have to talk about modeling. But Ahmed, if you want, you can send me some particular questions you have about tornadoes and I'll try to answer. And I can also direct you to some literature. Next question, lying down would also be okay. Much more uncomfortable than kneeling in the mud, of course. Even more uncomfortable. Yes, it's much more uncomfortable, but more likely you end up injured or dead. Because when you are lying down, you're covering much larger surface. You want to minimize, if you could, you want to levitate above the ground, but you cannot. So you don't want to have too many points of contact with the ground. Just like when you do something with wires, you don't want to use both hands if you don't have to, because if you get hit by light, by current, then the current will go to your chest. But if you use 2 fingers, then it's more likely that the connection will go through 2 fingers and maybe you survive. Now, the same is when you are on the ground, Well, you don't want to put your heart on the ground and then the current goes directly to your heart. Okay, so lying is not a good idea. What is the possibility a person can survive? Well, I cannot now, I cannot quantify, but of course, if you have some rubber shoes, it's much higher probability you survive. If you have, it was demonstrated, but this is often not the case. If you are somehow completely dry, it's also a much better chance, but you are most likely in rain. So being, or at least sweaty, running away from the rain. So in principle, it's, I don't know, I don't have a number, but it's not a good probability. Okay. Any other question? Okay. If not, I will see you Tuesday. That's the last lecture on modeling. And then during that lecture, I will also tell you about the exam and the format and how that will go. Okay? Thank you.
Thank you.
You're welcome.
Bye.
Thank you.